It's 13.
13. Okay.
It's written.
Sweden? Oh, yeah. Sweden. 102. 102 is the code for this course. I don't even know the code. I don't remember the code. All right. Let's begin then. Shall we? So, we are familiar with 1D integrals, Riemann integrals. They are defined on 1D intervals. So, when we do multiple integrals, the 1D integrals are replaced by 2D interval, which is a Cartesian product of 1D intervals. We call them the region of integration. Okay. I'm half sleepy. The 1D interval on which the Riemann integral is defined for a single variable will be replaced. So the 1D interval AB is replaced by a 2D set. We call this set Q generically, region of integration. We call this set Q throughout this topic, region of integration. It's our first class on multiple integrals. So first we will consider rectangular regions okay, and later we will consider more general regions with curvilinear boundaries rather than with curvilinear boundaries rather than rectilinear ones. Okay. So what is that we are integrating? So the integrand is a scalar field f defined, okay, and bounded on the region of integration Q. Okay. This integral, this one our the integral. Which integral? So the integral is called double integral, and is denoted by this or either of the notations. So the integral is first defined for step functions and then for more general functions. So first thing is partitions of rectangles. So these are like introductory remark. I call them. And that's our first topic after the remark, partitions of rectangles. So that's like a subtopic 2 or topic 2. Yeah. So it's topic 2 today, or topic 1, depending on what you call. So let Q be a rectangle. So first we have to define the region be a rectangle before defining the double integral. Okay, similar to the line integral, we have to define the curve on which we will integrate, and then the path, and then we define the line integral. Similarly, here we have to first define the region of integration on which we will perform the integration. So let Q be a rectangle given by a Cartesian product. Let me write it down. By a Cartesian product of two closed intervals. Okay. A, B, C, D. So which is x comma y pair, where the first entry belongs to the AB and the second entry belongs to CD. Okay. Now consider two partitions P1 and P2 of AB and CD respectively. So what do you mean by that? Okay, so you have a geometric picture in your mind, so you have ways to make them absolutely straight. However, I'm not being able to do that. So suppose this is called A and this is called B, this is called C and this is called D. Then you have rectangular region here, okay, which you can slice up. So how do we slice it up? So you're saying that P1 and P2 are partitions of AB and CD. Okay, so partitions means that you chop it up into a lot of smaller subintervals. Okay, call this x1, this is x2. Okay, this would be called xn minus 1, and this is called b. Similarly, chop this up. This would be called y1, this is ym minus 1. This one. Okay. So, say the way I described it, I could just write those points. So the endpoints are your partitions. Oops, write this point as well. Okay. Where x0 is A, xn is B, y0, did I said what? Okay, I forgot to put y0 here. Some reason. Y0 is C and y1 is D. Okay. So you just consider a lot of those rectangular segments. And many of them, I'm just drawing a few of them. I have to think about them. Others are there. So many the others. Okay. Now, P1 cross P2 is said to be a partition. So when I smoothly go from one page to another page, the problem is this is the boundary where I can write.
That means it is a connected set.
This is a connected set, yes, they're all connected to a partition of Q. P1 is like a one big thread of page without piecewisely connecting, joining a lot of pages.
It is supposed to be disjoint sets.
Yeah, they'll be disjoint. So if you cut and glue, if you are good at gluing, you can make smooth, but usually we are not. Okay, so P1 times P2 is said to be a partition of Q. Okay, P1 decomposes. Any questions? AB into n subintervals, and P2, as we can see, I'm just writing, decomposes n subintervals
A plus 1.
because you have x naught. Yeah,
Plus 1 point 0.
it will decomposes CD into m subintervals. That's why it's a rectangular region. Okay. Same but different. So therefore P1 times P2 decomposes Q into Mn subrectangles. That's obvious. So a partition P1, partition not P1, sorry, partition P prime. So partition of not an interval but Q. Let's say another partition I have instead of, did I call anything? I haven't really said, well, you can consider it as a P. You can call this a P partition. It composes P1 times P2 is equal to P. We call this a P. Okay. A partition of the rectangular region Q. Now, you can have another partition. The partition is not unique. You can have another partition where P1, P2 will be different number of P prime of Q is said to be finer than P if P is contained in P prime. Does it make sense? Okay. So you can make even smaller subintervals, okay, where these endpoints are also in that. Okay. So all the points of P are also in P prime. Okay, but it has more.
So here Q is just a name.
Q is
It's not irrational. Number 9.
Q is okay. What is Q? Q is defined here.
Just a rectangle.
Yeah, it's a rectangle. Okay, it's a rectangle. Intervals. So open subrectangles are edges missing. So here we have the edges. Just make it open. Then there's an open subrectangle. So the comment: open subrectangles. Yeah, when Q is a rectangle and these are smaller rectangles which are subrectangles. So open subrectangles are Cartesian product of subintervals, okay, without, with edges missing. Yeah, question?
Is it P primes, P prime contains in P?
No, P is containing P prime. That's why P prime is finer. P prime is finer. That's why.
Let's say if I take, let's say, 5.
As a set, this is bigger. Okay, it's bigger than P prime. It's bigger than. You have more elements then. The same rectangular region, but you chop it up in more. So you can make two. So what can be example? So you can have a chop up like this,
Yeah.
but you can make more chops,
Yeah.
make it more finer.
Yeah. So what does P do that example?
P is this chop. So you have like A, B, C. So you have A, B, and B, C are two chops in P. Here you have I don't know, A prime, B prime. These are also in P prime. Okay, so it has a more. It's finer in the sense they have more subintervals there. Okay. And every point in P is also in P prime. So yeah, okay. So in terms of
but say I took, let's say, one millimeter to 1 meter by meter, and then I take 0.75, then it is also financial, right?
yeah, my smaller you get. Yeah.
But,
So yeah.
but the elements may not be same.
No,
The example you're giving here is like, say, 50%, 50%. We have A, B, and we take an element between A and B.
okay. No, well, you can make another things actually. You can make even. You can make. Okay, you can switch it here. You don't need to keep them. You can make it even shorter. You don't have to fix them. It's just one example. So okay, so this is kind of close to what we do in topology. In topology, you can give many topology to the set. You have a set of elements. You can give many topologies. So suppose 1, 2, 3 constitute a set. So if you can give every one of them as an open set. Okay. So or you can say the whole set is just open set, not saying that 1, 2, 3 individually are open sets. So saying that every element of the set is an open set. Okay. So let's make an example of it. So you have this 1, 2, 3 is a set. So its power set would be like 1, 2, 3, 1, 2. I think I would just not write all of these things. It's just too much. I think that to make the point, I have to just write something like this, right? Obviously, empty set as well. Yeah. So it's 2 to the power 2 number of the power set. So I can say only this an empty set. So I can say, okay, this is my topology. These are open sets. That satisfies conditions of topology. If you take union and intersection, they are in the set. Okay, let me call this curly O. So that's a topology. So that's a topology on this set. Okay, but I can say all of them are open sets. All of these are open sets rather than these two only. So this is a finer topology than this. This is a finer. If I say all, yeah. More open source. Yeah, you see more information like this. Yeah. So this is finer. So that's an example. So this is if I call this O prime, then O prime is finer than O, and obviously O is contained in O prime, right? Okay. So another definition. The definition is of step function. Step function. Step.
You say same.
No.
It's different.
Okay. Yeah, it's just a step function. Right? It's not every side. Every side is a particular step function. But yeah, it's just a step function. And it's a constant on certain regions. Like you can have, right? These are step functions.
You said it's different.
Yeah. Yes,
Just
exactly.
unit step.
Yes. Well, it doesn't have to be unit. I mean, you can have arbitrary, right? The whole point is that every region you have a constant value, different from the other region. Okay. But in this case, it may be the same, maybe different. More general is that okay, if it is same everywhere, that's a constant function. But you could have more general situation. So there's a definition coming out. A function f defined on Q is said to be a step function if a partition P of Q exists, the partition P of Q exists such that F is constant on each of the open subrectangles of, I should have had a cup of coffee, I missed it. Terrible. What is going to happen is that I have to go to the next page. I must go to the next page. It's in a big diagram. Okay, so I have to, okay. So, too much. Okay, that's not going to do it. Really? Now, so what does it mean? So you chop it up into different regions. I made it worse for myself. I'm going to give only 6 of them. To make the point, make it as simple as possible. Not simpler, too simple, so that I miss the points, but let me use a different color here for the projections. And the okay. Projections like function value. So the z you can consider z as your function value, function of xy. Okay. Doesn't go that way. Jesus Christ.
This is an app store.
Yeah, this is an app store. So that's one particular slice, but you can make many more of them. For example, this is one particular value here. It's a well, so you have to think of it as a particular value, a slice here. Similarly, you can do the same for others. So, then you can have something like that. So the whole point is that we can have it a bit higher. So etc. So whole point is that everywhere you have some, for every patch you have the value of a function which is constant in that patch. Okay. So here it's a constant, here is a constant, here is a constant. It corresponds to this, this corresponds to this one. This corresponds to, say, this is 1, this is 2, this is 3. This 2 corresponds to, say, this one, and 3 corresponds to, similarly you have others. Okay. 3, 4, 5, 6, 11. Okay. That's all it meant. Defined on Q is said to be a step function if a partition of P of Q exists such that f is constant on each of the open subrectangles of P. That's the definition. Now, if I select, if f and g are two step functions on Q, then C1f plus C2g is also a step function. Okay.
Considering
Yeah.
they have the same partition or they can be any arbitrary partition.
Okay, so coming to that, if P and P prime are partitions of Q, okay, such that f is constant on the open subrectangles of P, okay, basically partitions of P, and G is constant on the open subrectangles of P prime, okay, then C1f plus C2g is constant on P union P prime. Does that answer your question? Okay. Therefore, so this is called a common refinement. Common refinement of P and P prime. The set of step functions form a linear space because it satisfies the property of linearity. Okay. Any questions?
It is called common refinement.
Yeah.
It's actually union.
Yeah, it's a union. It's union.
Right? So since it gets larger intervals.
But you have to,
Partitions.
yeah, no, F is defined on one partition and G is defined on another partition. But they're constant in different partitions. Okay? But F plus G is also constant. Okay, in there, when you take union, you have to take union because P contains one type of partition where F is constant. G, okay, so let me give an example rather than giving my hands. So suppose you have a rectangular region. Suppose F is constant on this partition. Okay, so this is not quite a partition. I have to give some, at least one of them. So this is a partition where F is constant. Now I can have where G is constant. So here G is constant and on the blues F is constant. Okay. So your region, suppose in this region you consider, in this region both of them are constant. Okay. But if you only had this region, if you only had region which is where F is constant, G is not constant there. This is the point. F was constant on these regions, right? This is a subrectangle, bluish ones. F was constant throughout, but G is on that patch. G is different, so you have to take union because G is constant on other patches, and on those patches F is already constant. Yeah. So therefore, this new partition is actually is a union, which is a common refinement for both of them. Okay. Now, common refinement বলার উদ্দেশ্য হচ্ছে because we don't know beforehand which is smaller, which is bigger. Is P prime? In general, in this case, well, when you have a cover, are you familiar with the cover and subcover in differential geometry? Cover and subcover. There is another definition of refinement. That refinement tells us that okay, what did they say there? Yeah, it comes around. So there you have a subcover, and refinement is that you have from that well, you have a cover, then you get a subcover, and the subcover. If you I think you have a finite subcover as a refinement. Even I forgot the definition. It's too tricky. Let me check that in the literature of differential geometry. Points remain the same. Okay, so give me a few moments. Yeah, it's a locally finite. That's the definition of a refinement, right? So if you have something which is infinite, then you make it locally finite. Then you call whatever infinite set, you made that a refinement in that. So that was a definition of differential geometry. Can you Google it and see what is the mathematical definition? Let's see if we can bridge this with this definition. Internet, so I might be able to get that. Refinery in a refinement. Manifold. Any hits? There is no wiki page for refinement, for definitions. So refinement of manifold data is a computational process which produces a denser set of discrete data from a given one. It is, so things kind of waste. I'm sorry? Yeah.
A refinement of the partition P is another partition P prime that contains all the points from P and some additional points, again sorted by order of magnitude.
Yeah, contained in P prime, right? Isn't it?
So P may P prime, it contains more points than P, additional points.
In this case, that's they are calling the P.
That's why it's a refinement.
That's what calling that. That's what they are calling refinement. That's kind of not the same in manifold. Make it locally finite and they call that a refinement. Maybe it is very weird. That's one definition. So manifold you can make it locally finite, even though you have a. So you, what is the idea? So you have a. So this is a manifold thing. It's a manifold, okay? Because locally Euclidean, right? You can have. So if you have a manifold, you need to have. You need to be able to coordinate. You need to be able to put coordinates on this patch, on this surface. Okay? So you can cover this surface by a lot of coordinate patches. Okay, a lot of open sets. Okay? So that's a cover for this manifold. Now it could be infinite, right? I could have infinite number of coordinate sets covering this. However, at a point, I can make it finite and call it locally finite. Only few of them I can keep here. Okay, so how do I do that? Well, I have an open set U. I take one open set and I keep only those open sets. Their intersection with my open set is not empty. Okay, I take one open set around a point and I take only those open sets. Okay, finite number of them that are covering that region around the P, but the intersection is not empty. So that's a refinement in.
I think that is what you define for interior points.
Let's not mix things up. That's a different thing. Yeah, but yeah.
I think
This is a roughly this is yeah.
But the sketch you are giving is the definition you give for interior points.
No, that's different. Uniform is for one open set. This is for a whole manifold. I mean, you can now give an argument that a whole manifold is an open set, but that's a different issue. Okay. Anyways, let us clarify. Yeah. So what are you saying that? Okay. You mean the finer is a finer refinement? We said the finer means a refinement. In that sense, the P prime was finer than P. Is that a refinement? Could be. Refinement. What does refinement mean? It's a common refinement, right? So what do you mean by common refinement? Well, it's a technical term, but it has a reason. What my understanding tells me that it has to refine things. It has to make things better understandable. You know? Yeah. Improve something. Perfecting something, right? Perfecting something. So here, so common refinement too. It makes sense in the common refinement. Yeah, you have more information. You have, so you can see things better. If you have a larger division, you can't see them. You can make smaller subintervals, you can see them better. And that's a final, yeah. So that's the idea, I think, the refinement here, that you can see things better. Okay. So,
That is what we mean by additional points.
I'm sorry?
That is what we mean by additional points.
That is what?
If you have same points, yet you have some additional points, which makes it the refinement for the set partition P.
Yeah. In the P prime, you have more divisions, right? More points. The union, right? Yeah. So
That's what you say. It's the common.
it's a common refinement. Yeah. So you have to take a union, otherwise your f plus g is constant in the union. Okay. Doesn't make sense. It makes sense that we explained, right? It has to be a union. That's why there's a common refinement. Which that's what I was saying. Which one is we don't know already. So it's a common refinement both of them. That should fix the thing. So it's basically the spirit of refinement that's important, rather than a particular domain where we have used it, maybe manifold or analysis. Okay. Good. So that was that. Now let's move to the next. Why did next? So that's a definition of double integral of a step function. So definition, which is a double integral of a step function. Step function. Okay, so that's the definition. Let f be a step function which takes constant value Cij on the
Isn't it like finite elements that you also say function?
But numerical integrations are different features.
yes, similar to that in spirit.
And they consider that
Yeah.
say functions constant.
Yeah, same spirit. Yeah. The construction is the same. Subrectangles xi minus 1 xi times y minus 1 yi. Okay. Right. Thank you. The double integral of f over q is defined by the formula this. Okay.
And there's a small mistake that yi is equal to xi.
In this case,
Because you don't see I.
well, this is just a generic example.
Yeah.
You cannot, it doesn't matter. It's just, I actually I don't have to make a change there. I am not defining anything, but I'm saying that one is before the other. So there it doesn't make a difference actually.
But if we take that, then we are just only summing over one plus that.
On the well, it's just an example. Okay. Well, so you can say that. Okay. Why I can say that? Because I have a Cij here. Then
Yeah.
the j is not quite accounted for. Okay. So ठीक है. Yeah, delay better. But at that place, it really doesn't. You have a Cij here. That's why it makes more sense if you put a j there. Yeah, I think
More consistent.
more consistent. Yeah, more consistent. I don't try to be too consistent, by the way. And usually I don't try to restrict myself. Too much restrictions doesn't help me see things. So
Creative mathematician.
Every mathematician, if somebody is a math, I'm not. If somebody is a mathematician, he has to be creative.
Yeah.
How can the thing is that you cannot be carried away by too much. Ideas are important in mathematics,
Absolutely.
but they cannot be wild ideas. When you have to express them in a way that makes sense. In mathematics, makes sense has a precise definition. Every step needs to be needs to have support. Needs to be
You need to tame your awareness.
yeah. In physics, however, if you have intuition and if you can compute something, if you have a result which is sensible, that's it.
Right.
People don't bother too much, but they should. Good physicists they do bother. There is another problem. If I say good physicist, Einstein was a good physicist, obviously, but he never bothered. What did I do? No. He never bothered too much about maths stuff. As long as f is constant, so very good. So we have a definition here. Okay. So definition is essentially the Riemann way of doing things, as you can see. Just generalize. As long as f is constant on the open subrectangles of Q, the value of the integral is independent of, so you should be worrying about it because we have taken a partition and you might be worrying, okay, does the integral really depend on the partition? Might worry about it. No? Actually, as long as f is constant on the open subrectangles of Q, the value of the integral is independent of the choice of partition. So you have this partition and you say, okay, P is constant here, but you can make more partitions and this is still constant. As long as you can find open rectangles where f is constant, it doesn't depend on partitions.
Is it the analog of line integral?
Exactly. Yeah, you chop it up. Yeah.
If we are taking that, how we parameterize it doesn't matter as long as the line integral is constant.
This is not actually here. We're not parameterizing it.
But how we're chopping it is.
Yeah, we chop. It's not the same. Yeah, it has the same flavor, but not the same thing. It's not parameterizing. Well, let me not use the word parameterizing it, but computing it in the region. So it doesn't matter actually. If it makes sense, it doesn't have to always have to be analogous to something else. Mathematics is very difficult always to make an analogy without, maybe it's not the same. We have encountered with refinement. In spirit is the same. It's not always in physics. Oh my God! Most of the time, you're very happy that it is the same thing.
Then we can prove there is a symmetry there.
In physics, everything is a spherical cow. But a cow is arbitrary shape. Well, not that arbitrary, but it is not very spherical, right? Symmetry is not very. But you start as a physicist when he studies a cow. Fast approximation is a spherical cow. It has a spherical symmetry. Then you perturb it with the two.
I thought that was engineer's stuff.
Yeah, physics and engineering is not that different, no? They're the same thing. Okay, so yeah. So for brevity, we choose a notation. Okay. Okay. It's not that physics is bad. Here, all the comments that we're making, we're really mocking. It's not right. Physics and engineering is good. The problem comes up when you just disregard something. Disregarding is not a very good idea. Somehow, science people that I met who doesn't do mathematics as a mathematician tend to avoid very tidy math arguments. What is the problem with tidy math arguments? Maybe it's because of their researchers. Maybe because they are researchers in a scientific domain, so their brain is exploring in that region. Now, if you put it in some other box, maybe it's not comfortable in it.
Goes across the board.
Yeah, so criticizing anyone is not very, yeah, that domain everybody is.
Anything new is always challenging for everyone.
So the thing only two both sides like p and p prime, they only enrich if you take common refinement. You combine all of them and you get something out for all of them. So modern mathematics and physics, they are going hand by hand.
Oh, yeah.
Modern day physicists come up with, they have this path integral that this is the integral. So path integral we have, but we do not have a very good mathematically sound definition for complex domains when path integral people do. Most of the fruitful results come from the complex domain. So
Hopefully, someday soon we have new mathematics
for path integrals, yeah, mathematicians,
I mean, I'm talking about for biological side.
yeah,
Biology was not really approached, and physics was approached.
yeah, biology would be, yeah, it's getting revolutionized, right? It's just, so yeah, so yeah, but exactly, so yeah, they can also contain certain ideas, but physicists already produce certain results that were not known to mathematicians. In modern day, okay, they produce certain results and then mathematicians come up and prove them in their ways. Physicists somehow got them before them.
So biology has to step up.
It is, I'm not sure how, because I don't know much of biology.
Too much of biology, but
Yeah, it can also pose different problems. Yes, exactly, absolutely sure. It should pose more problems for mathematicians to come up a good solution. So to remind ourselves, um, so to remind ourselves for this sum, says how for this sum, how this sum is formed. For this sum, to remind ourselves how this sum is formed, we write the symbol for the integral as this. So this is an alternative notation. Now here we are not saying anything infinitesimal, etc., yet. We're saying that this is just this. Okay. So if f(x,y), the function is constant on Q, that is on the intervals, open intervals, okay, we have okay. Now, what is b minus a? B minus a is this. What is this, right? So that means we have k dx dy. That also means because the f is constant throughout the region, I can do this. Okay. So these are 1D integrals. So these are this, not that whole of it, but this and this. These are 1D integrals. So here what we're doing is evaluating a double integral by iterated integrals or iterated integration. So first you do this, then you do that. So this is called, so later we'll see how to do it for functions, okay, which are not constant on Q. Okay. So these are called evaluation of a double integral by the repeated, I don't know why repeated is used. Maybe repeat means you have one-dimensional integrals you do at the same time. Yeah, these are one-dimensional integrals and you do perform another one-dimensional integral. Repeated or iterated integration. Okay. Now, follows from definition certain properties. So from the definition, so I'm going to like this definition. Okay, so definition I'm using this is shorthand everywhere, so I think it's okay. From the definition, the following properties follows. The following properties follows. What are they? Number one, linearity. Okay. So for any real number C1 and any real number C2, okay, if you compute this thing, okay, so from the definition means you chop it up again, sum, writing a sum, and you can prove this thing. Okay, so there's a linearity, you can say it's a linearity. So one comment was I could have said that the functions, step functions, they were forming a linear space. So integral you can think of, so what does integral do? If someone asks you, what does integral, is it a function? What is it?
Operator.
What is an operator? Do not, this is it's very common. What is it? Try something which makes sense, which what you do with integrals. What do we do functions? You have a independent, you have a dependent, you have sets. So for one set, it's a map between two sets. What is an integral?
It also a map. It also a map.
Let's define it for a scalar field, say. An integral is outputs a real number, right?
If it is a definite integral, then
Okay, let's say it's a definite integral. A definite integral is actually, you will make it, you can make it a definite integral. Yeah, okay.
By the way, that may be from my backdated primitive maths knowledge. Usually we define integral for the continuous function, right? But for discrete function, we usually go for summation and C plus n. Whatever is so in
The smooth wise, yeah, piecewise. Discrete means piecewise smooth curves.
this smooth also can define integral, right? But for
Yeah.
sigma summation, we only go for
I think what she was talking about, finite element method. So if you want to discretize it, yeah, if you want to discretize it, yes. So that's what we do. If you want to discretize it,
then you go for summation.
yeah, for discretizing it, yeah. And then you can take it, well, yeah, okay. Can you go from summation to integral? That's the question. If you, yeah, Yeah. Yeah. Okay, so you can, yeah, so the definition of an integral is in terms of summations.
Yes. And this supertail limit becomes used.
Yeah. So, yeah, but if you start from a sum, so integral, if it's well defined, then you can write a summation and do the things. Can you have a, say, discrete stuff? You can't go the other way around, right? You do not have the nice definition. You can't get to the integrals. So the question I was saying that the integral spits out a real number. When you are, what you're feeding it, it's a function. You're feeding in a function and you're getting a number. It's not a function.
But this is scalar.
Yeah, it's called a functional.
Functional.
It's a functional which takes in a function and produces a number.
So
As a scalar field map is
Eh.
also a function. Because
Yeah, scalar field is a function, right? You're plugging in into the integral and you're getting a number,
yeah,
a real number. Okay, so these are called functionals. Functionals act on, so the definition of functionals, they act on vectors. So if you Google Wikipedia, you will find the functionals act on vectors and gives you a real number. So these are this linear space they form, step functions. They're satisfying linearity property. They are functions. They are vectors, right? And you can take an integral of them, and you get a number. So that's a linear functional acting on them. So functions also form a vector space. Okay. So the integral is a functional. It's an example of it. Okay. Okay. So function takes in numbers, outputs number. Okay.
how is this
It's a function.
different from the scalar field map?
Scalar field takes a number and outputs a number.
No,
It's not a. It's a number.
It takes a vector. Right?
Yeah, it's a number. It's a vector valued number, but it's not a function null. Oh, you're saying that it's okay. You're saying that I see what you mean. So it's also taking input as a vector and then outputs a number.
Yeah.
So why is that? Is that a function null? Why is that a function null?
Yeah.
It's still a function because by okay. So this map is a map as a function. R into R. It's a map as a function. Now a function null is actually over the functions. And here it's itself a function. A function is over the functions, over f. Okay. So it's a good question. They have a similarity there. Okay. But you need a function to integrate over. You can't, it's a number. What do you do? You can integrate over it, but you get a constant.
Yeah.
Okay, so it's not the most general case. A function is the most general case for an integral to integrate over.
Suppose if we have indefinite integrals, then we are having functions. Which are
No, indefinite integral is not a function, not a linear function. You don't get a number, right?
Yeah.
You have to get a number.
So that then if we are taking definite integrals,
Yeah.
then we have functions.
The indefinite integrals are actually not. It's just what you know. Do not know the boundary. Ultimately, if you know the boundary, you will put the boundary value. Okay. So ultimately, you are looking for definite integrals, but sometimes you don't exactly know the boundary, or you just want to create a theory which is simpler to analyze. Then you put in the definite boundaries. Okay. So the first property is linearity. Second is the additive property. This is another interesting property. If you can chop up your rectangle into two subrectangles, okay, then your integral becomes this. Basically, it's very easy to prove. You just separate the terms. Okay, it's the additive property. This is something shared by thermodynamic extrinsic variables. It's additive property. Entropy is additive. For example. Additive. Yeah, yeah, okay. I'm talking about thermodynamic system, not information theory. Comparison theory. This is a comparison property. if Sx comma y is less equal 3x comma y for any x comma y in the rectangular region, and we have, so you have one step function which is less than another step function, or less equal, say, then, well, dx dy doesn't matter. Doesn't matter if you chop it up. Ultimately, this is a step function, so it's almost trivial here. In particular, if t xy is greater or equal 0 for any xy in the rectangular region, then okay. Now, more formalizing. Next thing, next topic. Yeah. Zoom. Can I cover all of this today? I probably can. Okay, so I'm going to go ahead and do this. I want to cover certain materials. The definition of the definite integral. So we are defining it for step functions, first of all. Okay? There's a similarly Riemann integral is also defined for a single variable of a function defined and bounded on a rectangular region. So in the rectangular region, I mean Q. Okay. So that's the topic. We have met the step function. Now we are talking about not a step function for any function, but it has to be bounded. Okay, yeah, it has to be bounded. Okay, it has to be bounded. So
that is none of the function scalar field value peaks.
I'm sorry.
Bounded means here that none of the scalar field value peaks.
Yeah, they're bounded. Yeah.
Or the total integration.
Riemann integral is defined for bounded functions in intervals. Okay. When you go to infinity, you have to check if the thing converges or not. What you're computing converges or not. So for example, if you put minus x 0 to infinity, it's okay because it converges. Okay. So ठीक है sir. So let f be a function defined and bounded on a rectangle Q. Suppose, so it is defined and bounded. Suppose the bound is something like this. Suppose, come on, the bound is this. There is an M which gives the bound. If number 4 body. Okay, 4. The region. So if you, so this is a bound. Clearly there is a bound M, right? M is a real number. Okay. So then you can understand that F is surrounded from above by what do you mean by above? So what is this? What this means? It means that minus m F is greater than minus m. From above is should be m. I'm sorry?
M belongs to real numbers.
Yeah, m is real number, yeah. M is some real number, yeah. Why did the word above come? When it's bound on the left, so why is it above? It's like from should be below, no?
TX square will be
Should be below.
from TX square.
Yeah, I think it should be from below, no? So did he write above? Okay, below বলে রাখছে হ্যাঁ লেখার সময় তো আমিও খেয়াল করি yes it's from above and from below it is a function so from above he says minus m from above what is from above
I think it's what it means is bounded above. Bounded below.
bounded above bounded below
The superior or inferior number.
yeah they will come in but yeah so how does bound from above from above by okay so what is from above so it's bigger than that in that sense the f is bigger than minus m okay it makes sense right yeah sorry yeah. It makes somehow forgot why so from above because this is bigger than minus m so it's bigger than that so above of minus m okay so yeah above by minus m so keeping this in mind okay minus m and bounded from below by what is that by plus where these are step functions s and t okay. Order let's keep the order fixed s and t are step functions okay so now we write the property okay so we can write this inequality more generally this way so we can write call this one it's very important for any small y in the region Next definition. So with this in mind, we can now define the integral. I think it's not definite integral. Is it definite integral? Sorry, should be double integral. I'm sorry, please fix it. So in the short note, I wrote DI. Forgot it's double or definite. So we was talking too much about definite discussion. I got it might be definite. The integral of a. How do people remember things? One thing they don't know how to remember, and those people who remember, when I consciously remember, they attach it to something.
Yeah.
Okay. So.
Like if you ask someone address, they will say, "Oh, তোমার বাসার পাশে এটা ছিল, তোমার বাসার পাশে এটা ছিল."
Yeah, that's how we define things, right?
Yeah.
আরেকটা ওয়ে আছে হচ্ছে তুমি চোখ বন্ধ করো, আমি তুমি এইভাবে এত স্টেপ রাইটে যাবা, এত স্টেপ লেফটে যাবা, মানে in terms of step without the surrounding, how he measured it. Okay, so one is looking at all the neighborhoods, and one is just telling you যে এখান থেকে এখানে যাবা, আচ্ছা এত স্টেপ রাইটে যাবা, এত স্টেপ লেফটে যাবা, এত স্টেপ রাইটে যাবা, তারপর
So one is path dependent, one is path independent.
yeah, it's more like Google ম্যাপে দেখায় না যে there's an algorithm, right?
Direction. It's direction.
So the integral of a bounded function over a rectangle. Okay. But even though that's pretty rigorous, it doesn't give you a lot of information. It doesn't tell you much. Okay, ওর বাসাতেই যাইতে হচ্ছে। Okay. If there is one, so and only one number, we call this I, such that this is less equal I, less equal this for every pair of step functions satisfying one. Okay, then this number is called the double integral of f over q. Okay. And it is denoted by now we are properly defining it for properly means we are defining it for a bounded function, okay, instead of step functions, but we are using the step functions to make the bounds clear. Okay, so we need the step functions to really come up with this definition, okay? Because when the step functions, we define the step functions, so we define the integrals of step functions, right? Then we are using them to define integrals for a bounded function and bounded by those step functions. Okay, so that's how it comes in. Step functions are tools. Yeah, boundaries. Yeah, they're tools which are giving us this. Sure. Good. Okay. So we just formalized it, we wrote it down. So bounded from above means that it is bigger than minus m. So it's above minus m and below plus m. So bounded from below in that sense. Same thing, but written for general functions, bounded functions, not step functions. When such an I exists, the function is said to be integrable on Q. So this is important. You just can't go ahead and given presented an integral. It's not always. You must check that is it integrable on Q or not. Okay. And such an I exists, then only then you can say this is integrable on Q. Satisfying. One means this one. This is an equality. Yeah? Then the next thing is called upper and lower integrals. Next topic. Now so you can understand what they will be, right? You can already guess what they will be. There will be those S and T integrals, upper and lower integrals, which are bounding my function integral. So let f is bounded on Q. Let S and T be two step functions. Satisfying one. That a set S, which is nothing but the collection of this I should not say two. Well, I said two, but don't take it the S and two are some fixed. There could be any step functions satisfying the integral. Okay, but two different types. So two types. Let's say two with the code. That means that they are not uniquely defined. They are whatever satisfies the inequality one. Okay, so you can have a class of values, right? Which are less than f, which are greater than f. Okay. So that's how I'm defining S. Where S is all of them which are less than f. The integral of which are less than f. Less than the integral of f. But they themselves also less than f. Okay. Not coming to that yet. Because they will satisfy this property. So they satisfy this property, they will satisfy this property. I should call it 2. Okay. Yeah. Question?
Should we also write down upper and lower double integrals?
Where? Where?
There, upper and lower integrals. Should we also write?
Yeah.
Upper and lower. I mean, upper. The title.
Yeah, this is upper and lower. Yeah, this is the title. Upper and lower integrals.
Double integrals should we write?
No, yeah, I will define it, then we'll see. Which is the upper? I haven't said yet. Which is the upper?
Double, because
Oh, I was upper about double integrals, it says. Oh, actually, yeah, okay. Well, everything is double integral here. Thank you. Everything is double. Yeah. So these are also, so yeah, here it's also, yeah, thank you. These are also double integrals. If anything, one-dimensional integral comes up, we will be curious and we will give it proper emphasis. We will compute it. We'll do that today, hopefully. Oh my God. My hope seems very bleak now. Let's see. That the watch does not exist. Formal argument মধ্যে আটকা পড়ে গেছে। They are very simple, by the way. Still, they're important. So, okay, we have this. Then by 2, condition 2 that we wrote down, that we have this, which is
everything
What?
is greater than t. Everything. Or should be less than.
I've written the other way around, right? I'm sorry. You're right. Thank you. Sorry, I should have written down this. T should be greater than F. You're right. So by 2, okay, let's not use by 2. Let me use this thing. Let me use if. How should I write it? Okay. For how should I write? Just write this thing. This is less than this. These are step functions, by the way. If s is less equal to, does it make sense? Because they're step functions, right? It's a comparison property. Then every element in S is less than, let me put it strictly less than then. It's less than every element in T, right? Therefore, S has a supremum, which means the greatest. That's why the word above or upper bound, greatest upper bound, and T has an infimum. Supremum is greatest. Is it lowest upper bound or? I always forget this. Supremum is the lowest upper bound. Doesn't make sense. Yeah, it does make sense. Lowest upper bound. It should be lowest. Yeah, should be lowest, right? Sorry, should be lowest upper bound. Yes, and T has an infimum. Infimum. That is the greatest lower bound. Greatest lower bound. Right. Thank you. In terms of upper bound, it must be the lowest one of all the other upper bounds. So the intuitive idea is that you have, so suppose x greater than 1 is a set. X is a set such that x is greater than 1. So how many numbers there are which are greater than 1? 2, 3, 4, 5, 10, whatever. But what is the supremum?
Depends on what.
Here the supremum is 1. Lowest upper bound is 1. Can you see? For this set. Greatest lower bound, lowest upper bound, lowest. Sorry, supremum. I'm going to say supremum. Yes, the lowest. Okay, so lowest upper bound. So you have a lot of upper bounds.
There could be more upper bound, but there's a lowest.
This is the lowest one.
Lowest one.
Yeah. Okay.
So here the lowest upper bound is 1.
1 because x is. Sorry. It's less than 1. Sorry, I thought it was less than 1. I was saying that 1, 2, 3, or 2, 3, 4, 5, they are all bigger than 1.
Then it is fair.
Because this set contains all the values from, well, not 1, less than 1, all of them are there. Yeah, so you're looking for the upper bound, which is the lowest one, which is 1, right? Supremum.
Infimum.
Infimum is the greatest, so, yeah, so I can tilt this one, can I?
Yeah. Yes.
So I have so how do I do this? So what do I mean by lowest? I can just tilt this one and I say, okay, what is the lowest upper bound here? Okay, do you get it? Why is the lowest no, not lowest, greatest lower bound. I'm sorry, I'm bad with words. But if you ask me to say, I just I can't say. Apparently, it's paradoxical. Okay, this is infimum. Okay, it is the greatest lower. It is the greatest lower bound.
Yeah, we got it.
Right, I got it right. Greatest lower bound. So you have a lot of lower bounds.
Yeah, true. It's 6:30.
Thanks today. Um, we are not even there. We have this little bit left.
Many more Fridays.
Yeah, that's also true. Okay, let me finish this one. Just upper and lower integrals, and that's it. It's going to take me like 2 minutes. Both here, 2 minutes. Sorry.
You already given folks like 90
Supreme.
Yeah, sorry. Yeah, is that so? Okay, yeah, okay. I was thinking of infimum, by the way, but anyways. So, okay, let's go. That's your hand. Okay, there you see. It's a boundary. And they, come on, they satisfy so S infimum T, and this makes sense. It makes sense because it is bigger, still bigger than S, but the lowest of them. And we say that S is less than T, that means obviously supremum is should be less than infimum of T. And infimum of T should be less than because the lowest, sorry, greatest lower bound. So, right? That's right. Okay. So what do we get? These three. Compare 3 and 2. This and this. 2 is this. And look at the definition also. The definition of a, there is one and only one number I such that this inequality holds for every pair of step functions satisfying 1. That means this. Okay, then this number is called the double integral of f over q. That's the definition of double integral for a bounded function, right? So now you see there are 2 candidates for it which satisfies this property. Okay, and if you have 2 things, that's not unique. So what you want, both of them has to be the same for the definition to be precise. Okay, because we define it, it has to be one and only one number. It is our definition. Okay, therefore math পড়তেছি না preach করতেছি আসলে convince করার জন্য all the emotions, it doesn't make sense. It shouldn't be like this, but as a human I don't know any other way. Sorry, f is integrable. No, I know I'm trying to be more robotic, but then you will say the class is not fun either, right? If I'm too robotic, if I am too robotic, I'm not excited, or I do not show any emotions, it would be very dull class. Yeah, that's also true. Therefore, f is integrable on q if and only if they are the same and they're equal to this. Okay. That I that we are saying, that I, that number. Okay, so no points for guessing actually. You already know. So this is called the lower double integral of f. Of f, and is denoted by I bar, lower bar of f. You see how it's written? It's a functional. It takes in function. So there is a bar. So okay, in the lower. So there's a lower. Is called.
Because we are using vectors
Okay, let's not go into this. This is just you understand from the context, right? It's not vector, right? Okay. Upper double integral of f and is denoted by this. Okay. Infimum of inf f. There are two of them. Infimum. What the hell? I'm sorry. Infimum of f, infimum of কোথা থেকে আসছে? Supremum of s. Supremum of s as a set. Infimum of t as a set. ওগুলো তো সেট থেকে আসে তাই না? মনে আছে না ওই সেটটা ডিফাইন করেছিলাম ওই সেট থেকে আসছে। Yeah. Sorry. So thus আমরা এটাকে সেট হিসেবে রিপ্রেজেন্ট করতে পারি। সো আসলে সেট হিসেবে বলতে কি এটা তো একটা নাম্বার হবে বাট এটা সুপ্রিমাম হবে ওই সেটটার তাই না? তো এসটাকে আমরা লিখতে পারি দেন সুপ্রিমাম অফ দ্যাট সেট এস রাইট which is defined for this where s is less equal f and this is this infimum of আচ্ছা আমি একটা থিওরেম লিখবো তারপর শেষ হ্যাঁ জাস্ট একটা থিওরেম লিখবো জাস্ট এবং থিওরেমটা আমরা প্রুভ করছি so this is the only theorem for the today's class and we have already proved it just এটাকে থিওরেমের মধ্যে লিখবো আর কি every function f which is bounded on a rectangle Q okay, has a lower lower integral লিখছি I think you would understand it is a lower double integral f and an upper integral I bar of f satisfying our second property. And the lower integral and upper integral satisfying. I'm sorry. So what I should have done instead of writing it because আমার তো আইটাকে না আমার আসলে এটাকে ইউজ করা উচিত. So I should be using them. So lower, upper. And then this is can I squeeze it there? I can't. So there is a big problem. For all step functions S and T with this is you need this is okay this is the requirement then the function f is integrable on Q if and only if okay its upper and lower integrals are that's what we saw right these two must be basically infimum and supremum and infimum of S and T. So for S you take supremum, for T you take infimum. Okay, because for T you want the greatest lower bound, and for S you want the greatest upper bound. Exactly right. Okay. Lowest upper bound. Yeah, is it? It's the greatest upper bound. You go to the infinity. Sorry, I'm saying it, but these words I don't know. Maybe I don't get it.
So you're saying that this upper and lower integrals are equal?
Yeah, they must be equal. They must be equal.
If the bounds are equal, then the rate is zero.
I'm sorry.
If bounds are equal, like from
No. The bounds are there. These bounds are there.
okay.
These intermediate bounds, they must be equal.
Oh.
Because in between them, there must be one. There must be one number in between them. There must be the integral. Okay, so when you go to that's why you need supremum and infimum. Okay, you squeeze from here, you squeeze from there. Okay,
They should be equal.
and that should be the same. Sandwiching it. Okay? There's only one number between them. Step function গুলো তো হচ্ছে particular constant value নিবে. Okay, right? So constant value গুলো তো range আছে অনেকগুলো. আমরা পুরো সেটটাকে কনসিডার করছি। ওই সেটগুলোর মধ্যে এমন নিব এমন অবশ্যই of course exist. That's the supremum and infimum. They exist, right? They do not have to be in the set. That we saw in the example. They don't have to be in the set. So exactly we will find that these two are same. And that is the integral. That is our double integral. Okay? Otherwise it is not. This is our definition. Otherwise it doesn't make sense. Step function construction will not help us to the same na hoy. Okay? So that's the thing, and then that means well, we have in which case we have this. So we have proved this already, right? And we're just writing as a theorem so that we can say it fancily. We have a theorem that it is proved. Okay, so ঠিক আছে. That's it for the day. Meet next Tuesday, right? Hopefully we can cover more materials next Tuesday.
And happens if you call integral operator as well.
I'm sorry?
As it happens that you can call integrals operator as well. These operators do have a strict definition.
Operators don't have?
A strict definition. They can be generally considered as functions, mappings. So you can say that integrals are indeed, like he said, they are strict that it's no operator. And functionals are a sort of function. So it's like rectangles are quadrilaterals, that sort of things.
Yeah, but I have to go back and check much more about operators. But the thing, operators are maps. Okay, so
Functions are also function. Taking their argument as function.
Yeah.
Functions are
It's so
oh yeah, functions are.
Functions are also function. Because their argument is a function.
No, that's not the definition of a function. A function, functional, yeah, functional takes it well. So that's the functional is so the construction is that functional acts on vectors. So it's a vector space element. Vector space is a mathematical construct. Now you know it, right? You know it from linear algebra. The vector space is a mathematical construction. Vectors are the elements. Functionals, linear functionals, whatever, they act on vectors and produces number that belongs to the field where vector space is defined. On which vector, okay? Over the field. So these functions, yeah, I'm trying to beach them instead of islands which are not connected. You can use it in other contexts, but you have to be precise what you're doing. Here I'm saying that these functions form a vector space. Okay? So they're vectors. They are vectors, right? They are vectors because they form, the vectors. Okay, because you can add them, they satisfy linearity property. Okay, so this is in that sense it is a linear functional because they act on functions and produces real number. Okay, in that sense. Now operators are maps. Yes, that's true. Functions are also maps. Okay, so but what? Okay, so operators. Okay, there are this called and. Okay, so operators can either take you from one space to another space. Okay, or they can map. So you know linear algebra. The idea of a linear operator is that it takes you from. Well, can it take you from one vector space to another vector space? It can, right? There are linear operators that carry you from one vector space to another vector space, but they are not endomorphisms. The endomorphisms are which takes you which is a mapping to itself, right?
Yeah, I don't know about this, but I think the first order predicate logic language and very weak at it because I need to capture. And also this set, I need to do a lot of hard reset for my set kind of ones.
No,
I struggle with it.
yeah,
I don't know about this.
yeah.
I think it's really important to have this first order predicate logic.
Yeah.
Language very clear.
Yeah.
Whereas I struggle with this.
They're everywhere. It's
these are the fundamentals, and the actually is a foundation.